Okay, so welcome to lecture number 8. Just 1 minute, somebody's. Okay, so welcome to lecture number 8, and today we'll talk about the poles, zeros, and concept of stability. Okay, already we talked about poles in yesterday's lecture, so I'll take a recap of that one, and then we'll proceed further. And in today's lecture, we'll talk about zeros, concept of zeros, and then concept of stability, and then how basically the performance or response of the system changes by changing the location of poles and so on. So that we'll study in today's lecture. So yesterday we talked about the stability of a control system, like for example, stability can be your absolute stability or relative stability or this one limited stability or marginal stability and so on. So that we are going to study in detail in fourth chapter. Okay, in due course of time, we will study also the definition of stability and concept. Yesterday we talked about this one, the standard form of this one transfer function, which is given by y of s by x of s. That is, y of s is nothing but the Laplace transform of output variable. This is x of s is nothing but the Laplace transform of input variable. So if it is in this form, okay, and this one, the denominator roots of the denominator of polynomial are called as poles, because at that location, if you put the value of that roots value of s, which is equal to the roots of denominator, then that transfer function becomes infinity. That's why it is called as the poles. And the roots of numerator polynomial. So this is the numerator polynomial. So if you find the roots of this numerator polynomial, those roots are called as zeros. Okay. So if you put the value of s equal to that root, then the whole transfer function becomes zero. That's why it is called as the zeros, okay, of the system. Also, I talked about this one. Poles are represented by cross and zeros are represented by 0. Okay, and system order is basically is nothing but what is the maximum order or highest power of s in the denominator. So that is nothing but the system order. So system order is equal to the number of poles of the transfer function, and this transfer function is having nth order because highest power of s in this transfer function is n. So that's why this system is considered as a nth order plant or nth order physical system and so on. So that is what we have studied in yesterday's talk. Also, we talked about the poles definition. So pole is defined as it is the frequency at which system becomes infinite. Means if you find out the roots of this equation, then if you put the value of s in the whole transfer function equal to the root of that denominator, then the whole transfer function becomes infinity. Value of that transfer function becomes infinity. So corresponding roots are called as the poles. So poles is defined as it is the frequency at which the system becomes infinite. So whole transfer function becomes infinite, and hence the name of name pole is given, and so on. Whereas zero is the frequency at which the system becomes zero, or the roots of this numerator. If you find the roots of this numerator and if you put the value of s is equal to that root of that numerator, then that whole transfer function will become zero, and so corresponding roots are called as the zeros of that system. Okay, so the poles of the Laplace, okay, we have seen here also, yesterday we have seen this example also, that the poles of the Laplace function are the values of s that makes the Laplace transform infinity, or whole transfer function infinity. So they are therefore the roots of denominator of the polynomial. Now look at this one. So in this transfer function, 10 into s plus 2 divided by s plus 1 in one bracket and s plus 3 another bracket. Now in the whole transfer function, this 10 is nothing but the system gain, open loop gain, and this s plus 2 is nothing but the root of the numerator, which is nothing but the 0, And there are two roots in the denominator, so there are two poles. One is located at s is equal to -1, and another one is located at s is equal to -3. So there are two poles. One is located at -1 and another one is located at -3, whereas there is one zero which is located at -2. Okay, so these are basically the real poles. So sometimes it may happen that there are complex poles, okay, or complex zeros may be there, because if roots are complex one, then those okay, denominator roots are called as the complex poles, and the numerator roots are called as the complex zeros. So complex poles always appear in the complex conjugate pair. So there will be pair of complex conjugate, and the transient response of the system is determined by the location of the poles. So we'll see how the transient response of that system, or transient is nothing but the time response of the system, how it varies with the location of poles, that we are going to study in this lecture also, right? So this also we have studied in yesterday's talk, so that's why I'm taking too fast. So poles is also defined as it is the frequency at which system becomes infinite. So at that location, okay, or s is nothing but the frequency at that location, your system transfer function will become infinite, and corresponding value of root of that denominator is called as the poles. Now, in today's lecture, we will study the concept of zeros, and then stability, and then how basically the response, transient response, changes with the location of the poles, and so on. So that we are going to study. So as I told you that the zeros of a Laplace function or a transfer function are the values of s that makes the Laplace function evaluate to zero, or they are therefore the zeros of numerator polynomial. Means basically if you find out the roots of numerator, okay, those roots are called as zeros. Now in this earlier example, 10 into s plus 2, as I told you that this 10 is the open loop gain, s plus 2 is the numerator root which is called as a 0, and in the denominator there are two roots, one is s plus 1 and another one is s plus 3. So these two roots are called as poles, whereas the numerator roots is called as 0. So this 0 is located at s is equal to -2. So in a given transfer function, there is one 0 and there are two poles. So this 0 is located at -2. So complex poles, complex 0 may be also there, which will always appear in the complex conjugate pair, and so on. Right. So what is the relation between poles and zeros and frequency response of them? So the relationship between the poles and zeros and the frequency response of a system comes alive with the 3D pole zero plot. So, so this is basically a single pole which will give you the response. So if the value of s is equal to that this one root, then your response will be infinite response, and then so that's why it is called as the pole basically, right? Now, consider this example. Consider the transfer function of this system, which is given by y of x of s by y of s, or sometime if you are considering x of s as input, then this will be a denominator, and we y of s is output, it will be in numerator. Okay, so which is equal to c into c divided by a s plus b. Now see that this is the root of the denominator. So the denominator polynomial as plus b. So what will the value of s? Value of s will be equal to minus b by a. So if you take b to the right side, so it will be minus b, and then s will be equal to minus b by a. So this pole is located at minus b by a. What about this one, zeros? There is no at minus b. The only pole of the system is located at think there was some problem with the this one. Okay, I'll record. Can you tell me from which slide, okay, this presentation was not visible? Somebody?
So slide number 11. After that it was
Okay, just it was okay. Just means this one, this slide. Right. Fine. Fine. Okay. Fine. Okay. So this was the slide number 11, right? Okay. Is it visible to everyone now for board division?
Yes, sir.
Okay, fine. So I was considering this example, transfer function is given by C by AS plus B. So this is basically the root of this denominator, and this root of denominator AS plus B is nothing but S is equal to minus B by A, because if you take AS equal to minus B, and then S will be equal to minus B by A. So this pole is located at minus B by A, right? Now, see that how do you basically how do you represent these poles and zeros on a complex plane? So I told you that zeros are represented with zero sign, and poles are represented with cross. Like for example, if this is zero, now see that this is complex plane, means it consists of real part and imaginary part. So this real part is on x-axis and imaginary part is on y-axis. Now consider this as a one unit. Okay, so this one unit is left unit is, suppose for example, this is -1, -2, -3, and to the right side it will be +1, +2, and +3. And for this one it will be plus j1, plus j2, plus j3, and for this lower side it will be minus j1, minus j2, and minus j3. Now this says that there is a zero which is located at -2, right? And this says that there is a zero which is located at -3. So this is on real axis. So this is real axis zero, which is located at -2, and another one is located at -3. Now, if you consider this one, this pole, this is a pole. Okay, so what is its real part? Real part is -1, and what is its imaginary part? It is plus z2. So this is located at -1 plus z2, and another pole is there which is located at, see, what is the real part? Minus j1, and what is the imaginary part? It is minus j2. So minus j1 minus j2 is the location of this pole, and this location of this pole is minus j1 plus j2. So these two poles are complex conjugate poles. Whereas suppose for example, if it is this is a imaginary pole, imaginary zero, then this is located at +1 plus z3 if it is z3, yeah? And then this one will be equal to +1 minus z3. So like that way we can plot a poles and zeros in a complex plane. Complex plane consists of real axis and imaginary axis. So you know that S is equal to sigma plus j omega. Sigma is nothing but your real part, and j omega is nothing but your imaginary part. So these are basically real zeros, and then this one is complex pole, and this is also complex zeros, right? So I hope that you have understood how to plot the complex poles and zeros on a complex plane, right? Have you got it? Yes, please. Oh, is it? Am I connected or disconnected again? Am I audible to you people? Yes, please.
Yes, sir.
Okay, so have you got the concept of, okay, how to plot the poles and zeros on a complex plane? Yes or no? If yes, okay, otherwise I'll explain it again.
Clear? Yes, sir. We got it.
Okay, fine. Okay. Now, see that. Suppose, for example, okay, there is a pole here located at this -3. So S plus 3 will be located at this -3. Okay. Now, how will be the response of this system? See that 1 upon S plus 3 is the transfer function. So at the denominator, there is a S plus 3. Okay. So S plus 3 uh, means if you take the inverse Laplace transform that one, it will be e raised to minus 3t, right? E raised to minus 3t. Now, if you plot the this one time response of that one, e raised to minus 3t. So by putting the value of t, various value of t, like when t is equal to 0, okay, you will get the response like this. And as t goes on increasing, so it will be exponentially decreasing. So see, this pole is located on the left hand side of S plane. So this is the basically left hand side of S plane, and this is the right hand side of S plane. So now this pole is located at the left hand side of S plane. Okay, and this is located at -3 because 1 upon S plus 3 means this is S is equal to -3. So if you take the inverse Laplace transform of 1 by S plus 3, it will be e raised to minus 3t. Now, if e raised to minus 3t is there, and if you put the value of t, various value of t ranging from 0 to infinity, when it is 0, so e raised to minus 0, that will be equal to -1, and then it will be 1, and then after that, as t goes on increasing, its response will start decreasing and it will reach to 0. So when there is no input, your output will approach to 0. So this system, see that when poles are located on the left side of S plane, your system is stable, right? So now this is on the left hand side of S plane, and this is on the real part, okay, real axis. So the response of that system is like is like this, right? Now, suppose for example, we have a pole which is complex conjugate pole. What is the value of this pole? It will be equal to -1 plus Z2. So this pole is -1 plus Z2, and this pole is -1 minus Z3. Okay. Now, if you put the value, okay, if you plot the response of this one, so there will be basically, that sinusoidal term is associated with that one, and the response of that pole with respect to time will be like this. Sinusoidally, it is decreasing. So sinusoidally, it will be decreasing. When there is no input, it will try to reach to the zero value. And as I told you that if poles are lying on the left side of S-plane, system is stable. See that it is reaching to the zero value, right? When there is a absence of input and so on. So your system is bounded basically, right? So this is imaginary pole, which is plotted here. And this is complex conjugate pole, and its response will be sinusoidally decreasing, like so damped oscillations, sinusoidal oscillations will be there. Now, another there is there. Suppose, for example, there are poles, but now these poles are on the right hand side of S plane. So see that this is the right hand side of S plane, and these two poles are lying on this. See, complex conjugate poles are there. So what is the location of this one? +1 plus Z3. So this is the coordinates of this pole. What about these coordinates of this pole? +1 minus Z3. So complex conjugate poles are there. And if you plot the response of this plot, okay, we are going to study all those things in our fourth chapter, how to plot in detail by putting this different values t. So it will be sinusoidally increasing. When there is no input, it is increasing with respect to time, and then amplitude is increasing. So sometimes it may happen that at time t equal to infinity, your output will reach to infinite value, and then your system will break, and hence your system will be unstable. So conclusion is that when poles are on the right side of S plane, system becomes unstable. Your output will be sinusoidally damped. This one amplitude will be increasing as time t goes on increasing, and so on. So for the system to be stable, your poles should be on the left side of S plane, whether it is a complex pole or whether it is a real pole. But if poles are shifting to the right side of S plane, then that system becomes unstable and your output will reach to infinite value even if there is no input and so on. So this is the behavior of unstable system, and as I told you that this is the behavior of stable system, this is also behavior of stable system and so on, because those poles are on the left hand side, but now this pole is on the right hand side of S plane, so it will be unstable system. Now if poles are lying on the imaginary axis, okay, so you will get the sinusoidal output, but it will neither increase the amplitude nor it will decrease the amplitude. So your output will be having constant amplitude. It will not reach to infinity or it will not reach to zero. So such dynamic behavior of that system, okay, is there when that system is marginally stable or limitedly stable, because when poles are on the imaginary axis of the system, okay, that system is considered as a marginally stable. When poles are on the left hand side of S plane, then that system is considered as a stable system. When poles are on the imaginary axis, then that system is considered as a marginally stable. But if poles are on the right side of S plane, then that system is considered as an unstable system. So if poles are lying on the right side, system is unstable. If poles are lying on the left side, system is stable. If poles are lying on the imaginary axis, then that system is called as marginally stable or limitedly stable, right? So here you get that, see that effect of location of pole. What happens if poles are lying on this axis, okay, or on this part, your system will decay fastly, okay, so there will be faster decay of the response when there is no input. But what will happen if the poles are lying on the right side of S plane, then there will be faster blow up, and it may happen that at t equal to infinity, your output will also reach to infinity. So your system will be unstable to this side, your system will be stable in this side. And here, if poles are on the imaginary axis of S plane, then there will be oscillations. Neither it will reach to zero nor it will reach to infinity. So neither we can say that system is stable nor we can say that system is unstable. So it is in between stable and unstable, which is called as marginally stable or limitedly stable. So this is the effect of poles. If you change the location of poles, if all poles are on the left side, system is stable. If any one pole moves from left to right, that system will become unstable. Or any one pole which is lying on the left side and it comes on the imaginary axis, that stable system will become marginally stable or limitedly stable. Or if it jumps to the right side of S plane, that system will become unstable system. So I hope that you have understood what is the effect of poles location and so on. Right now, see that tell me whether this, consider the following transfer function and determine whether the transfer function is a proper or improper, and also tell me the poles of the system, zeros of the system, and order of the system. Okay, now as I told you that the power of, see, for proper transfer function, power of denominator must be greater than power of numerator. Now what is the power of numerator here? It will be 1. What is the power of denominator? It will be 2. So if denominator power is higher than numerator power, then that system is considered as a proper transfer function or proper transfer function. So your first example is having a proper transfer function. Second thing is that what are the poles of the system? Now in this example there are two poles. One is lying s is equal to 0, one is lying at the origin of the S plane, and another one is lying at the s is equal to -2. So there are two poles in this example. One is lying at s equal to 0, another one is lying at s equal to -2, right? So we know the, okay, we have got the answer of first question as well as second question, means this is proper transfer function. Second thing is that there are two poles. One is located at s equal to 0 and another one is located at s equal to -2. Now we'll see the third question of this example, zeros of the system. So how many roots are there in the numerator? Only one root is there. So there is only one zero and where it is located at s is equal to -3. So if you equate this one equal to 0, so s value will be equal to -3. So there is 1 0 which is located at -3, right? And order of the system is nothing but the order of, or basically highest power of this denominator. So this if you solve this one, so it will be s square plus 2s now. So highest power of denominator will be equal to 2. So order of this system is 2. So we can consider this as a second order system. So this is second order system. It is proper transfer function. There are two poles which is located at s equal to 0 and s equal to -2, and there is only 1 0 which is located at -3, and order of the system is 2. So I hope that you have understood this first example, right? Now second example, we will find out same thing, whether it is a proper or improper transfer function. Definitely the power of denominator is higher than the power of numerator, so it is a proper transfer function. So this is proper transfer function. Second thing is that how many poles are there? So number of roots in the denominator, there are 3 poles. One is located at -1, another one is located at -2, and third one is located at -3, right? So there are 3 poles and located at -1, -2, and -3. Then third question is that zeros of the system. So there is only 1 0 which is located at s is equal to 0. That is nothing but at origin. So there is 1 0 at origin. What is the order of the system? So if you basically multiply this one, so it will be, I think, third order system, right? So highest power of s will be 3. So this will be third order system. I hope that you have understood second example, right? Now come to the third example, which is given by g of s equal to s plus 3 raised to 2 and s into s square plus 10. Now see that if you expand this one, so it will be s square plus 3 into 2, that is 2, 6s plus 9, right? So highest power of numerator is 2, whereas here highest power or denominator is 3. So we can first answer of this problem is that this is proper transfer function because power of denominator is higher than power of numerator. So it is a proper transfer function. Then what is this one? Poles of the system. So poles of this system will be like, there will be complex conjugate pole for this one. So there will be 2 poles here, complex conjugate, and then there will be 1 pole at origin. So there are 3 poles in total, right? In this example. What about this one? Zeros of the system. So this is repeated 0 at s is equal to -3. So how many repeated are there? 2. So there are 2 zeros in the system. In this system, there are 2 zeros in this system, which is located at s equal to -3. Okay, and what is the order of this system? So highest power of denominator is equal to s raised to 3. So this is third order system. I hope that you have understood example number 3, right? Now we will see the last example, example number 4. Now see that here g of s is equal to s square plus s square into s plus 1. So if you find, or if you expand this one, so highest power of numerator will be 3 s raised to 3 plus s square, right? Whereas highest power of denominator will be equal to s square. Now denominator power is less as compared to the numerator power. Hence, this transfer function is improper transfer function. This system is going to be unstable system. And so answer of the first answer is that it is improper transfer function. Then what is the second answer? Poles of the system. How many roots are there? There are 2 roots in the denominator. One is at 0, s equal to 0, and another one is at equal to s is equal to -10. So there are 2 poles. One is located at origin and another one is located at -10, right? Now, what about the zeros of the system? So there are basically 2 repeated zeros at the origin and 1 0 at -1. So in total, there are 3 zeros here because 3 roots are there in the numerator. And and what is the order of the system? So highest power of denominator, that is equal to s square. So this is second order system, right? So I hope that you have understood this one, the concept of proper improper transfer function, poles, zeros, and order of the system, right? Now see that. So the stability of a control system As I told you that uh, uh, this one, see, this is the S plane, and you know that S equal to sigma plus j omega. So this is left hand side of S plane, and this is the right hand side of S plane. Sigma is your real part, and j omega is your imaginary part, right? So this S plane. Now, if all poles lies in the left hand side of S plane, system is stable. If any one pole lies on the right hand side of S plane, system is unstable. If any pole lies on the imaginary axis, system is marginally stable. So stability of a control system, right? See that if all the poles of the system lie in the left half plane of the system is said to be stable. So this, okay, the location of pole, if it is in the left side, stable system. If it is on the right side, if any one pole goes to the right side, system is unstable. And if poles are lying on the imaginary axis, system is marginally stable. I hope that you have understood the concept of stable, unstable, and marginally stable. Now, see that, for example, g of s is equal to c upon as plus b, and if a is equal to 1 and b is equal to 3 and c is equal to 10, so this will be 10 divided by s plus 3. So definitely there will be one root in the denominator, and that is one pole located at -3. So this pole is at left hand side of S plane. There is no pole on the right side or imaginary axis. We can directly tell that system is stable. So this given system is stable because the pole is lying on the left side of S plane, right? Unstable behavior is basically if pole goes to the right side or pole location is on the right side of S plane, then that system output will reach to infinity when time t is infinity. So the output of process grows without bound for a bounded input. So even if you have given a bounded input, your output will be unbounded and your system will become unstable. Okay. So if the real portion of any pole of the transfer function is positive, the process corresponding to the transfer function is unstable. Means basically if that pole is lying on the right side of S plane. If pole is located on the right half plane, the process is unstable or that system is unstable, right? Now, okay, quickly we can say that determine the following transfer, consider the following transfer function and determine whether the transfer function is proper, improper. I hope that you can do it on your own. Already we have taken such kind of example. And then other definition, as I told you that we are going to study in detail the concept of stability in our fourth chapter, but just for understanding purpose, okay, definition of this one stability is that system is said to be stable if for bounded input means limited input. Okay, we have bounded input, your output should be bounded. So for bounded input, your output is bounded, then that system is said to be stable. Also, if there is no input, your output should reach to 0. So thus for any bounded input, output either remains constant or decreases with time. So that system is considered as a stable. See that this is the bounded input, right? And then you have given that one to the plant and your output is also not reaching to infinity and so on. So such kind of system is considered as a stable system and so on, right? Now, if for any bounded input output is not bounded, then that system is said to be unstable. If or for bounded input, if your output is unbounded, means it is going to infinity, then that system is said to be unstable, right? So this system is said, see that this if transfer function of that system is 1 upon s plus 3, so pole will lie at -3, so definitely this system is stable. But if system is having transfer function as 1 upon s minus 3, so if s minus 3 equal to 0, so this pole location will be on the right side and your system will be unstable. So this is the example of unstable system, this is the example of stable system and so on, right? Now, okay, just for your understanding purpose, this is the response of your system of 1 upon s plus 3, so it will be e raised to minus 3t. So if you put the value of t, various value of t ranging from 0 to infinity, so in the absence of input, your output will reach to 0. But here, if it is like this s minus 3, then see that transfer function is e raised to 3t. And if you, okay, in absence of input, as time t goes on increasing, so if value of t is ranging from 0 to infinity, this value will approach to infinity. So your output will be reaching to infinity even if there is no input. So such system is said to be this one unstable system, whereas such system is said to be stable system, right? So this is the output of your e raised to minus 3t. So it will reach to 0 if in the absence of input, but in case of e raised to plus 3t, it will reach to infinity in even if there is no input, but as time goes on increasing. So whenever one or more than one poles are in right hand side of plane, the solution of dynamic equation contains increasing exponential term, and hence that system will become unstable system, and so on. So overall, what we have studied is that we have studied Laplace transform, then we have studied transfer function, we have studied the order of the system, the concept of the poles, concept of the zeros, stability of the system, and bounded input, bounded output. So this finishes our chapter number 3, and from tomorrow we'll start our chapter number. We have finished our chapter number 2, and from tomorrow we'll start chapter number 3, that is mathematical modeling of physical systems. So that we are going to start in our this one from tomorrow's lecture. Now, okay, there will be assignment. You have to submit the assignment, and then that assignment is everybody has to solve the problems on Laplace transform, forward Laplace transform, as well as inverse Laplace transform. 10 problems on this one Laplace transform, and 10 problems on inverse Laplace transform. Everybody's problem should be different. If there is copy, or basically if there are two similar kind of problems, then marks of both candidates will be deducted. So take care of that one. And time given will be 1 week for you. So next Tuesday you have to submit the assignment in Google Classroom. So I'll share that Google Classroom to you people, and in 1 week time you have to submit 10 problems on Laplace transform and 10 problems on inverse Laplace transform. So that will be your first assignment, right? So we'll stop here. If you have any question, you can ask. Otherwise, we'll call a day. Yes, please. Any question from your side? Okay, fine. So shall I close that one? Okay, then I'll close today's meeting.